All right, so, okay, now let's go on to event scheduling. You might remember we did event scheduling with the greedy algorithm. So clearly this is different. We're adding on weights to the events. So I guess the weight is profit. It's some events pay you more, right? And so our goal is to find a subset that don't overlap, but our cost now is the sum of the weights of the ones that you schedule, right? Everybody see the difference, right? So here's an example, and all of those examples, our greedy criteria was to look at the event that finishes first and schedule it, right? And but of course, yeah. No, it's an input, the arbitrary number, right? So here's an example, right? That job doesn't want to be, it messes up 2 other events. Yeah, but they're paying a lot, right? They get what they want, right? Does that make sense? Right, so this algorithm clearly doesn't work. All right, so let's do the game of life again and see how people like the game of life method, right? We're just, what's Pooh Bear going to remember? He's going to go through the events in some order, and he's just going to remember which event he's on, right? Which event to look at next. That's all he's going to remember. So he could say, he's at event I, right? So there's some order, and he's about to look at event I, and he could ask the question, what event do I take next, right? And the bird could say, take event K next, and we would have an edge from event I to event K, right? Everybody get that? Now, you might see I haven't really built this example up much, and the reason is because we're not going to go with it, right? Anybody? I guess the bottom line is remember I had that slide that talked about, do you want long edges or short edges, right? Or what are we doing here? Are we doing long edges or short edges? It's kind of a long edge, right? Because you go from some I all the way over to some K, right? And how many such edges are there going from some I to some K? Right? How many choices are there for I? N, right? N choices for K, right? We suddenly have N squared edges here, and the running time of our algorithm is really the number of edges. So we don't like this. We don't like so many edges, right? We want fewer edges. So instead, we're going to ask a smaller question, right? This is sort of a complex question. What event do I take next? What are we going to ask instead? It's still back to which event, right? You know all the events, but you're just wanting to know, what about the solution? Both of your questions are questions about the input, right? And we know the input. So the solution we don't know. The fairy godmother knows the solution, right? And so we could ask her, from event I, which event do I take next, right? But what's an easier question? Oh, again, which is the last event? She still has impossible answers, right? The problem is she has too many answers, right? Here, the number of sub-instances is in, and the number of bird answers is kind of in, right? So the number of sub-instances times the number of bird answers is in squared, right? So we're going to want to have fewer answers for her to give us. Like, let's make it a yes/no question, right? Then there are 2 answers you could give us. Can you ask her a good yes, no question? You're standing at event I. What's a good question? Yeah, or even do I take the event I'm standing on? Right? Do I take event I? Right, exactly. Or the next one. I mean, it's the same idea. All right, so you're standing on event 1, right? And first we have to know which event is event 1. All right, because how did you sort them? So do we want that to be event 1? Probably not, right? This is just at some point on a slide I said computational problems are more likely to have a good dynamic programming algorithm if the things have a nice natural order, and jumping in the middle here just seems a stupid thing to do, right? So we're not going to do that. We could sort them by starting time, or we could sort them by finishing time, right? And here, which one goes first depends, right? And this is kind of where it got me wrapped up about turning things around, right? Because you turn it around, start time becomes finishing time, right? So you had to think, you had to ask, well, which of these do you do and why? I'll tell you, one of them is going to work and one of them is not going to work, right? And what does that look like? What does working look like? What does not look like working look like, right? So the greedy algorithm went for finishing time. So let's do that and see what happens, right? So we're going to sort by finishing time. And here I numbered a few of them just so we remember the order, right? Here I've ordered them by finishing time, right? We start with event 1, and what are we asking the bird? Do we take it? Do we take it? And she says no. She says no. That's pretty easy. We delete it, right? Yeah. The bird is a non-deterministic superpower of magical abilities, and she knows what the right answer is, right? But that's not our problem right now, right? Our problem now is when I do the bird friend algorithm idea, then we try all the bird answers, right? But we're not doing that even now. Now what we're doing is we're making the graph, right? So we're going to put in an edge for every possible answer, and we're not going to give any thought whatsoever as to which answer is going to be best, right? So if she says, delete it, where do we go? Yeah, we just go over to the next event, right? And here's where we start giving a little thought to. It's not just that I'm standing on a state which is considering a particular event. I kind of have to know what the subproblem is, right? And the subproblem is going to be what's the future, what's remaining for me, right? when we ask about the end, it'll be what does we give our friend. But going in this direction is what's remaining for me. And what's remaining for me is the subinstance. How do I got events 2 onwards, and which of those do I take, right? That's going to be this instance state here is going to correspond to the subinstance. Consider events 2 onward. What do you take of them, right? Does that make sense? So that's pretty straightforward. Now, if she says yes, then we take it. But remember, if we take it, what can't we take? Anything that overlaps with it, right? So those events, if you see who overlaps with it, it's those events, right? So what subinstance do we have to solve in the future? Right? This, right? We have to say, hey, friend, right? Hey, future, how do I got event 3, 4, 5, 7, and onward, right? Which of those do I take? But does that feel like a nice subinstance? No, it's a horrible subinstance. And you know, we think about what would we call it, right? What we would call it is some subset of the events, right? And if it's an arbitrary subset, how many subsets are there of a set? Right? It's an exponential number. If I have n objects, right, then do I take the first object or not? Two choices. Do I take the next object or not, right? They're the 2 to the n subsets, right? Yeah. We so far, we considered the first event. The bird said, take it, right? And because we took it, we had to delete 2 and 6, right? Does that make sense? Right? Right? And the problem with this is that the number of subinstances would be exponential, right? And in the old slides, I given an example where we look at the events in a funny order, not this order, and I show an exponential number of subinstances, right? So we don't want to do that. And so let's abandon ship and try something else. All right, everybody understand what the problem was there, right? So we're going to abandon ship and we're going to do it by start time. And so now we have a different order. And just as before, the bird says, no, we delete this event. And just as before, the rest, what we have left to do, our subinstances, events 2 and onward, right? And so that's great. We can call that, you know, here we call that event subinstance 2, right? We're in state 2. We're considering event 2. All future events are still possible, right? And that feels good to us, right? But then she says yes. So we take 1, right? Now we delete everybody that overlaps with 1. And that's all of these guys, right? Now, what's the improvement here? Yeah, I don't care about the size of the subinstance. Same as smaller. They're ordered, right? In fact, it's I was going to say prefix because I'm usually going the other way around. It's a postfix, right? It's what do we want to name this event? Well, what do you want to name it? Is I'm ready for 6, and everybody in the future, all the other ones are possible, right? So here I am. I'm ready for the 6th event, right? And all future ones are still possible, right? The point isn't that it's smaller. The point is that it's prettier, right? It's ordered. It has a nice name to it, right? Hence, there are fewer of them, right? Everybody get that? Now we have to say, was that a coincidence, or is this really is going to always work for us, right? Right. So what we're going to claim that it always works, and what do we mean by it always works? Is that the remaining subinstance is, oops, there, see, I'm so used to prefix, is a postfix, right? It's always a considered as a postfix of the events, right? And so what do we need? Here we're saying, suppose J overlaps with I, right? We're asking about event I. We took event I. And if J overlaps with I, then we delete J, right? And if we delete J, then we want to delete, right? Right here, we deleted 5. What do we want? We want everybody before 5 to also go, right? Does that make sense? So if we delete J, then we want to delete everybody, right, between I and J, right? Does that make sense? And we're going to do proof by picture, right? Here, let's see what's our proof. Here we go. There, that is the line where event I here ends, right? And we're sorting them by by start time, right? So in general, the start times of these events are this direction, right? So how do they have to overlap? They have to overlap with this line, right? They have to overlap coming this way, right? And so let's consider them. Okay, here. Oh, here's 6. 6 did not overlap, right? Here I'm coming backwards. 6 did not overlap, and we're sorting them by starting time. So there's that one. That's why did 6 not overlap? Because it's on the right of that purple line, right? But then 5 did overlap, right? But we keep going in order. So 4 did overlap, and 3 overlapped, right? And 2 overlap. They overlap because, I mean, we're doing these backwards in order of finishing time, right? So once one of them overlaps, since we're going backwards in terms of finishing times, they keep overlapping, right? Does that make sense? Right? And so now we have to say, what costs do we put on these edges, right? It's how much does this event, this action of moving forward, contribute to the cost of our solution, right? And anybody have an answer? What value do you want to be putting on these two? Here we're not taking the event, so it's 0. And here we are taking the event, except the event is worth W, I think. Yeah, I wasn't sure if it was a V or a W, but it's a W, right? Does that make sense? And then similarly, we're here, and we can say, do we take it or do we not? And she says, don't take it. And so that's our next event, right? And if she says, do take it, right? Then those all get overlapped, and we go over to, I guess this one here was 11. All right, everybody kind of buy that? So what are our states? These are the states we were talking about, right? What is the subproblem 5 is I have event 5 and onward, 5, 6, 7, 8, and I want to schedule them, right? And all right, so what happens if she keeps saying no, right? She keeps saying no. Here I'm having this be the state, right? We're always, for each event, we go to the event that's next in the order of sorting them by starting time, right? So this is just the path where you always go to the next one, starting time. Oh, look at this event. This event here seems to get lost out. We should have gone from here to here to here, but everybody good with that? And what are the yes edges? The yes edges go from each event to the next event that doesn't overlap with it, right? So, right, this guy here, it goes up here. Why? Because it overlaps with this one, and it doesn't overlap with that one, right? Everybody kind of buy that? She says, yes, go to the next event that's still alive. And that gives us a graph, right? Yeah. No, you're always starting at the first event. Yeah, I'm just, really those arrows are down here. I just thought putting them up here would show you better where they go. Really, our starting point is here, right? And there's a yes, a no edge and a yes edge, right? And the last here is done. You consider them all, right? So this is S, and this is T, right? Does that make sense? And you can imagine if any path through this graph, tells you which ones to take and which ones you not take. And the cost of the path would be the sum of the weights that you've taken, right? And we've made sure that the solution corresponding to this path doesn't have events that overlap, right? And similarly, any solution of overlapping events, non-overlapping events, correspond to a path. Yep. Yeah, so our task has nothing to do with paths, nothing to do with birds. Our task, if we're doing a reduction, our path is simply to construct the graph, right? So what we're going to do is we're going to have these states, which says, the state says, I'm ready for the 6th event, and I'll have an edge leaving it. If my bird would say no, I have an edge. If the bird would say yes, I have an edge, right? Yeah. Yeah, we don't have a bird at all. We're just setting up the graph, right? We're saying if I was ready for the 6th event, and if I had a bird, and if she told me no, then I would go past the 6th event to the 7th event, and I wouldn't add anything to my cost, right? And if she said yes, then I would have to come all the way over to the 11th event because all these events in between were deleted, right? So I just set up the graph, right? Now that I have this graph, what do I want to be true about this graph? I want there to be a one-to-one mapping between every solution to what's our problem is a subset of events that don't overlap. That's a solution, right? So for every subset that don't overlap, I want there to be a path, right? And for every path, I want there to be a subset of events that don't overlap, right? And I want their cost to be the same, right? So you can imagine, suppose I gave you a solution, i.e. the bird has a solution, and those are the answers she's giving you. Then you would follow the edges that she specified, and it would give you a path. And the value of the path would be the value of the solution, right? Similarly, if I had a path, right, the path, first goes this way. Well, that tells me I'm taking the first event, right? So the path corresponds to a solution. The solution corresponds to a path, right? So my problem was to find the best solution, but we're going to do a reduction here where I'm trying to come up with an algorithm for solving the best, which events to take, right? So here I'm given a bunch of events and I want to know which ones to take, right? So I just make this graph, right? It's all very local, right? Locally, I make these decisions for every possible event, sorted by starting time. I put a node, and then from each of those nodes, I put 2 edges, one which takes one step with a weight of 0, and one which goes to the next event that doesn't overlap, right? And I form this graph, right? Then I give this graph to the oracle. And by magic, the oracle tells me the longest path, right? And the longest path then corresponds to the best solution of our, right, which tells us which events to take, right? Does that make sense? Yeah, so I would say whenever there's a tie, you have to assume that it's you could say I flip a coin which one to take, but you could assume that the adversary tells me which one to take. And why is that? Is because I want to prove that for every possible input, my algorithm works, right? So my adversary is sort of giving me this input. And if he gives me an input with two start times that are the same, he's giving me the power to choose which one to go first, right? So he's probably not that nice, right? So he could just shift one of them by an epsilon, right? And it wouldn't change the result at all, but it would force us to take the one that he wanted us to take, right? So I would say whenever there's a choice like that, you need to kind of prove that your algorithm would work no matter which one you went for, right? Does that make sense? Then what's the running time, right? The number of states is the number of events, which is the number of sub-instances. And then we multiply that by the degree of, right, the thing, which is the number of bird answers. And that's, right? So now we're going to turn it around, right? And when you turn it around, now we're coming backwards, right? So if you're coming from this direction, we want to take the event that finishes last, right? Because in this direction, it starts last first, right? So we take the guy, this one here that finishes last, and we ask the bird, right? Do we take it? Do we not take it? And she says no, we delete it and we give the rest to the friend. And if she says yes, then we delete it and we delete everybody it overlaps with. And what we proved before was that what we give the friend then is going to be a prefix of what we had before, right? And so our sub-instances will be all prefixes, right? As a general rule, if your sub-instances are an arbitrary subset of your objects, right, then you're going to have an exponential number of sub-instances, and that will be bad, and the whole thing will be incomplete, right? And if somehow your sub-instances are a prefix because there's this nice ordering, and we maintain this nice ordering, then everything's fine, right? Everybody good with that?